Really excited to be here today with Daniela Roos and Pieter Abbeel. Thank you both so much for being here. I'm sure most people watching or listening are pretty familiar with both of these folks if you're following robotics, but Daniela is a professor of electrical engineering and computer science at MIT and director of the Computer Science and Artificial Intelligence Laboratory, which most folks probably know as CSAIL, at the same university. Her research spans across all of robotics, everything from soft surface robotics to human robot interactions to autonomous driving. So quite an interesting spectrum of different topics that we can talk about today. So very excited about that. And those not familiar, Pieter is the director of the Berkeley Robot Learning Lab and co-director of the Berkeley AI Research Lab at the University of California, Berkeley, just across the way here. I'm currently in San Francisco. Pieter is also the co-founder of Covariant.ai, which looks to bring some of the research that he's been doing with his group at Berkeley to real-world applications in fulfillment centers and beyond. He's also the host of the Robot Brains podcast, which if you haven't listened to, I highly recommend it. If you're looking to learn more about robotics, it's a pretty darn good place to start. And both the folks have been cited thousands of times, are at the forefront of robotics, and we're so delighted to be here together today. So Pieter and Daniela, thanks so much for joining me.
Thank you for having us.
Yeah, glad to be here.
Well, kicking things off, I think it's always fun to talk to people like yourselves about sort of the origin story, right? You both have been working on robotics for quite a long time, but presumably there was some point early in your life where, you kind of caught the robotics itch. So would love to hear where things started and what brought you from that initial point of interest to today. So maybe starting off, Pieter, what was your kind of first moment of, oh, wow, robots are interesting. I think this is what I want to do for my life's work?
Yeah, I often think about that because it's a common question. And it turns out for me, it really goes back to, I was in my undergrad degree in Belgium studying engineering. And I thought kind of almost everything's quite interesting. It's hard to eliminate any topics, what to even focus on. Everything's so exciting. And ultimately, what I got most intrigued by was essentially how people can think. The fact that we can think and do smart things somehow smarter than other animals is really what intrigued me the most. And then the specific evidence that intrigued me the most was the ability to build a computer program that plays chess. IBM did that at the time, to build a computer program that could beat the best human chess player. And this notion that somehow it's possible to program something that is better than yourself. Like you can play chess at some level, but you can actually write a program that plays chess at a higher level than you can play yourself. That to me was just really intriguing, and that's really what got me into AI as a whole, and from there into robotics.
Yeah, it's the point around how smart humans are is a very interesting one. I was having a conversation with a friend recently about how amazing it is that humans are the smartest species of animals on Earth, and we can make iPhones. And then number two is monkeys, who when they use basic tools and learn basic language, we kind of lose our minds. So it's a pretty insane delta between kind of us and the rest of the animal kingdom. Danielle, I'd ask you the same question. Where did it all start for you with regards to, I guess, to Pieter's answer, not just robotics, but AI more generally?
Okay, so remember when Mickey summons the broomstick in The Sorcerer's Apprentice? So I loved this piece ever since I can remember. And it's a piece that shows you can bring to life, you can animate everyday objects by magic. But it's really extraordinary that today you don't need magic to make that happen. You need robots and AI. And this is because of advancements in the field. It's also because of people's imagination and inspiration. And so for me, that was an exciting starting point about that launched this the fantasy. So in other words, I went into robotics because I wanted to work on something that brought together the world of mathematics with the world of physical things. And I was interested in autonomy. I was interested in both the engineering side of autonomy. In other words, how can we make the broomstick work? But also in the science of autonomy. In other words, what might be the biological foundations of autonomy. And so I wanted to understand the mathematical and biological foundations of autonomy, and also build machines that embody these functions. I was inspired by the possibility of developing machines that give people superpowers and help people with physical work. And I really do like to imagine a future with AI and robots supporting people with cognitive and physical work, with the same pervasiveness with which smartphones support us with computing work today.
Yeah, and building on that, Danielle, a lot of your current work is around kind of the interface between robots and humans, right? Whether that's controlling robots through gestures, controlling robots through brainwaves, which very much ties into what you just said around giving people superpowers and summoning things and all of that good stuff. Could you share a little bit more about what you're working on in that domain and how you're thinking about what might develop there over the next couple of years?
Yeah, so I'm very excited about a number of things. And in particular, since you started with human-machine interaction, I would observe that the machines we have built today, or up until today, are such that we have to adapt to them rather than the other way around. But in order for AI and robotics technologies to permeate society, we have to turn this upside down. We have to start building machines that adapt to us rather than the other way around. And so I'll get to your question about what we're working on, but I want to observe that the first industrial robot, called the Unimate, was introduced 60 years ago in 1961. And this robot was invented to do industrial pick and place operations. Now, between 61 and today, 60 years later, so many industrial robots have reached so many applications. We have tens of millions of robots that are being deployed. And these robots are masterpieces of engineering that can do so much more than people. Yet these robots remain isolated from the factory floors because they're large and heavy and dangerous to be around. By comparison, organisms in nature are soft and compliant and much more dexterous and intelligent. We have the octopus, we have the elephant trunk that can move with agility, they can bend and twist compliantly. And so I would like to have machines, I would like to have robots that have the same kind of properties, the same kind of features. And so a lot of my recent work is in the space of soft robotics. But more broadly, I am also wondering about how we're going to move from 60 years of the field of industrial robots to the next 60 years, where we will have robots in human-centric environments and robots helping people with physical tasks. Now, if you think about the predominantly deployed robots today, they are humanoids or they are robot arms. So they are greatly inspired by the human form, or they're boxes on wheels. And if you look at nature and even the built environment, we have such a broad variety of shapes. So I believe that the next 60 years will bring us machines that come in a broader diversity of shapes and that can be made out of all the materials available to us. This includes woods and plastic and engineered materials and paper and ice and even food. So my lab is developing computational approaches for designing such robots that are made out of a variety of materials that includes silicone and paper and food, also how you build the bodies, but then also how you create the brains that enable what the user wishes the body to do. And among the applications we're building these days are robots that swim like fish and move like turtles, robots that brush your hair, robots that pack your groceries, and can reason that you shouldn't put milk on top of lettuce. Robots that can recycle, robotic pills that enable incision-free surgeries. In each of these examples, we have to think about the body of the robot, we have to think about the brain of the robot, and what is the interaction between the robot and the users. And so these are the ideas that we are building on right now.
Yeah, and I had a chance to watch the video of the fish swimming around. And as someone who wanted to be a marine biologist growing up, I was a swimmer as well. I'm pretty excited to see some of the applications of that. And you touched on some really interesting stuff, Peter, that's actually quite relevant to what you all are up to at Covariant around, having robots coexist in locations where there are also people, some of the implications of how you do that in an effective and safe way, as well as some of the considerations around, if you're building a robotic pick and place arm, the real competition is not another robot, it's a person doing the same job and being able to do that job with the level of efficacy or better, as you mentioned in the chess example earlier. So I'm curious, as you've taken some of the stuff that you've done in the lab to these real life situations, what has been the same or different when applying some of the work you've done at Berkeley at Covariant?
Yeah, I think at a high level, in many ways, it's similar, of course. There's robots and they need to be smart enough to do new things that they haven't done before. But then when you look at the details, it's actually very, very different. When I look at the work that we do at Berkeley, and more generally, the work that's done in, I would say, academia and more generally publication-oriented work, it's really emphasizing novelty. It's about going places that we've never been before. We've never built a certain type of system before, and getting the first signs of life of something that people thought would maybe not be possible, but now all of a sudden here is some evidence that this is becoming possible. And that's a lot of the excitement about academic work, and it's a big part of why I love it so much. But then when taking it into practice at a place like Covariant, and I'm sure similar in other companies that bring robotics into the real world, the real challenge is not to show for the first time a robot doing something. It's about achieving really high reliability. And this becomes especially difficult once you move into environments with variability. So of course, the millions of robots we already have in the world doing useful things, they tend to be in confined environments mostly, where you can pre-program them to do certain motions, and that'll be productive to help build a car, let's say, or help build electronics. But if we now want to take robots into more open-ended spaces, let's say warehouses, or maybe help on a farm or help in construction, those are semi-structured environments where the robot will always be faced with something new. And so just repeated motion is not going to succeed. Now the robot has to see, understand what it's looking at, react to that, learn from that. And so when it's faced with all that, at the same time, it still has to be super reliable. Otherwise, it's not creating any value. And so when I think about the work at Covariant specifically, it's about how do we achieve many nines of reliability for whatever the robot is supposed to be doing, even though the robot is faced with constantly different items in the warehouse, different configurations, and so forth. And so it's a very different kind of challenge oriented around reliability compared to a lot of the academic work. Definitely the work I do in academics is oriented around novelty rather than reliability. Of course, it doesn't always have to be a strict split, but that is definitely a big difference I see between my two worlds here. And the reliability is just important, otherwise you're not useful as a robot.
Yeah, I would just like to add to that. That's absolutely right on the line, because at universities, we really want to uncover new truths. We want to do something for the very first time ever. And so showing feasibility of a solution for a new type of problem is the focus. But then taking that solution from the research lab into the physical world is a huge step. That involves a lot of issues around robustness and use cases and the kinds of things that we usually don't worry about when we prove the first solution.
Yeah. And with research, you're doing things that are these big, audacious problems, right? That in many ways people don't believe can actually be done. Has that, I come from first working in companies and now, of course, being at a venture capital firm. So I come from more of the let's take a thing that exists and productize it, which I think is largely what you're kind of getting at, Peter, with taking the research and making it robust in a product that you can package up and sell to someone, and it will run on their own. So I would imagine that the non-linearity of the research side can actually be both quite enjoyable and at times very challenging and stressful. So as researchers, have there been challenges in your career? Have there been particular obstacles that you've had to overcome? Have there been people that have doubted some of the things that you're achieving, and kind of how do you deal with thinking through, right, like these audacious ideas and going after them when there's a likelihood that it won't actually work out? So Danielle, I'm curious if there's any learnings for your career that you would share with aspiring robotics researchers out there on how to approach the nebulous nature of research, I suppose.
Well, I tend to like working on things that other people are not working on, and I also tend to like to think about a long time horizon for research. And here I'm talking, I don't know, 5 to 10 years out. And sometimes things work out, sometimes they don't. But when they don't work out, you just kind of have to understand why not. And usually, um, if you work on a new problem, any kind of result, whether it's positive or negative, sheds some kind of light in the space that you are working in. And there's some value to be made. If something doesn't work out, then you can ask why not. What are the assumptions that need to be introduced in order to have a solution for the problem you're really trying to solve? And so this sounds kind of abstract, but it sort of works. And let's see, what else can I tell you? I'm also very interested in how some of these solutions that are developed with a long time horizon, how they can matter today. So sometimes we work on topics that are really hard computationally or hard from an engineering point of view, but then they yield solutions that all of a sudden find their way in other in specific application domains, so that they can be relevant today. So I like thinking about both aspects. I will tell you, for a while we were working on programmable matter. So we were working on the idea that maybe you can have some universal particles that come together and can form any shape you want. This is in the spirit of the thesis I explained earlier, that the robot body is equally important in how well the task gets executed. And so we were trying to build these robots that could lift identical units and help each other kind of shuffle and reconfigure from one shape to another. Maybe we wanted a snake to go through a tunnel, but then we wanted a slinky-like shape to climb stairs, or we wanted to grow a long arm if we wanted the robot to reach up on a shelf, and we wanted to do this just on time. And it turned out that lifting things was very hard with the mechanisms we had available. And so what we did at that point was to say, well, let's work in an environment where we don't have the weight issue. And so, in fact, that was the starting point of our work in underwater systems. And in some sense, that was a precursor to the fish that you have seen just recently. Initially, we wanted to see whether we could have systems that could self-reconfigure and self-organize in water. We ended up building that, but then we also ended up pivoting and finding our way towards making underwater robots that are much more like the natural fish we have in situ than the robots that have been built to date.
Yeah, that's a great reframing of, I guess, the question I was trying to ask, actually, which is, anything you do has exhaust, and even things that don't work out, the exhaust of that experience teaches you a lot, right? And even in very simple machine learning models, if you're trying to decide which feature should go into detecting fraud, and you learn that certain things aren't relevant to detecting fraud, it's actually very interesting information, right? That helps you paint a clearer picture of the problem, even if it's not included in kind of the final machine learning model that you might build. And so I like this framing of, what are unexpected avenues that you've gone down that maybe haven't worked out exactly the way you thought, but led you in a different direction, which you mentioned with the fish. Pieter, I'm curious if there's been areas of your research where you've kind of gone down a particular path and maybe that path is dead-ended, but it's branched off into something a bit unexpected?
Yeah, I think at the big picture level, everything Daniela said really resonates, and so I don't want to repeat it too much. But maybe to frame it in a slightly different way is there is definitely ups and downs in research. Sometimes things move faster, sometimes they move slower, because that's the nature of it. But ultimately, the right kind of research will ask a question. When you're working on something, you ask yourself a question that you don't know the answer to, and you typically hope for the answer to go one way rather than the other, because often one way allows you to build something impressive and the other way allows you to realize that you cannot yet build that impressive thing, unfortunately. But even when you realize you cannot yet, you learn so many lessons. And so I think the secret to research progress on the academic side is really to ask the right questions. And that's hard. It's hard to come up with the right questions to ask. That's kind of, in some sense, what it means to be a successful PhD student and ready to graduate, is you're ready to ask the right questions and know what question to ask next. And then have a fast turnaround in getting answers. And so sometimes I would say at a meta level, the biggest research lesson learned for me is, as a PhD student and later as a professor, is to work on projects where we ran a large experiment where we could have learned the same lesson with a smaller experiment. And that's really where you move slower than you could have, because you could have maybe come up with a small experiment you can program up in a day and learn the lesson, and instead you ran a big experiment that took a week or 2 weeks, and now you learn your lesson at 10 times slower pace. And so I think being really smart about zoning in on the question you're actually trying to learn about and making somehow setting up the smallest possible experiment, I think, is key to making really fast progress. Now, sometimes I still get carried away. To your question, Bryan, like one thing that comes to mind, a project we worked on 3 years ago now was hierarchical reinforcement learning, which is still something a lot of research is done on today, but not a whole lot of progress has been made. But we were pushing on it really, really hard. We thought, okay, clearly the future has hierarchy. The future AI systems will have it, so we should try to make progress on it. And it just wasn't really working the way we hoped it would. And so we learned a lot because it wasn't giving the benefits we hoped it would. But then we started asking the question, okay, what benefits are we really hoping for? Well, we're hoping for the benefit that a hierarchical system, after it's been learning for a while, can learn more quickly in the future, right? That's what it should give you, faster learning in the future. And then that told us effectively, oh, actually, why don't we change our research direction to directly focus on how can we pre-train such that later the system learns faster. And we set up end-to-end optimization, which is something called learning to learn or meta learning, where the system is learning to learn fast. And now we actually achieve that same result of learning faster in a very different way. And I think those are the kind of interesting things that happen. Your first hypothesis of how to get there might not work, but you keep asking the question, and then you find a different formulation that actually gets you there.
Yeah, and this might be a difficult question to answer because it's a case-by-case thing. But how do you know when to, when it's time to pivot? Right, because in companies, you usually have pretty concrete feedback, which is like, people are not buying the thing that you are trying to sell. You're like, great, question answered. I should probably try to sell them something else. Is there a similar thing in research? Is it more abstract? How do you think about that part?
Well, I think that when you try to work on a problem and it doesn't give you the answers that you're hoping for, you have to understand why not. And in the process of understanding why not, you might discover that it's the wrong problem formulation, or that the problem is too complex for today's methods, or that the problem doesn't make sense for other reasons. And so at that point, you ask yourself, well, what have I learned so far? And what kind of new knowledge can I continue to discover based on that?
Pieter, is it similar for you?
Very similar. It's it's one of those interesting things with research where something not working, even though it's in one sense a little bit disappointing, in the other way, it's exciting because you learn new things. Now, of course, if it's not working because there's a bug in the code, that's a different thing. But if it's not working because the experiment is not going the way you thought it would go, it's actually often where things get exciting. And yes, it might help you change direction. It might force you to change direction, but it's an exciting change. It's where you say, oh, wow, this is something we hadn't thought of. And thanks to our experiment, we might be onto something interesting that, somebody who has not run this experiment might not even be thinking about this. And so we're onto something unique here, and makes it really exciting.
Yeah, it's a good life lesson, really, in being open-minded and checking your assumptions rather than, having a picture in your mind, a picture in your mind of how you want things to go. So transitioning quickly here to kind of the classic question in robotics and machine learning, which is kind of the future, right? Of all areas of machine learning, I think robotics is one that has received the most dystopian movies about it. Though of course, more general AI with things like 2001 and all that, there's a good amount there as well. But we're obviously kind of quite far away from the world where we have like fully autonomous, human-like robots. So with that in mind, how do you think, I guess the first question I ask is, how do you think the relationship between robots and humans is likely to change over the next 5 years? And how do you think the sentiment of people with regards to robots has changed over the past few years? So anything at all kind of around that. And maybe Danielle, we'll start off with you.
Okay, so when I tell people what I do, I usually get one of two reactions. So some people get anxious and they start making jokes about Skynet and wonder when they are going to lose their jobs. And other people ask me, when is my car going to be self-driving? Okay, so I'm a technology optimist, so I'm much more in the second category than in the first category, but that doesn't mean that we should dismiss the worries and the concerns of the first group. And so we need to understand where the concerns are coming from. We need to understand how to provide alternative perspectives on how to think about things. And that starts with understanding that AI, machine learning, robots are tools. They are tools by the people, for people. And like any other tools, these technologies are not intrinsically good or bad. They are what we choose to do with them. Now, some people end up choosing to do bad things, and we really have to think more deeply about how to prevent that for the future. But in general, I'm a technology optimist. I believe we can all dream of a better life supported by machines. And but I also want to recognize that this is a difficult time to be a technology optimist because many people are suffering, and so why should they care about smart machines? And what I would say to that is that machines have been supporting us through the pandemic, through machine learning for rapid development of vaccines and therapeutics, through new designs for effective masks, through contact tracing, through telemedicine. Even the Zoom session is enabled by technology. But as we struggle forward in this crazy changing world, I believe that robots and AI can help us unlock our human potential as individuals and as groups. And if we design machines thoughtfully with the potential risks and dangers in mind from the very beginning, then we will enable things that we couldn't even dream about a few decades ago. And so I don't think that the machines will steal our jobs. I think that the machines will spark the creation of new and more exciting jobs. And we will team with machines, and we will be stronger and healthier by creating the appropriate division of labor between people and machines. And this division of labor depends on understanding what machines are good at and what they're not good at, and what people are good at and what they're not good at. And so if I were to simplify this in the most concise way, I would say that machines have speed, but we have wisdom. And so it's possible to think about a world where machines can take care of some of the routine tasks that people don't want to work on, and have people focus on the tasks that require wisdom, that require the kind of intelligence and the kind of emotion and empathy that people are good at and machines are not.
Yeah, I'm inclined to agree with you. We're all technologists here, and I think as a result, technology optimists. And I think for me, it's very similar to what I imagine folks felt like during the Industrial Revolution, right? You have all these machines now that are taking labor that was previously done manually and took it into a more automated fashion. And that came with certain externalities that we had to resolve over time. And to some extent, we're still resolving some of the negative externalities of industrialization, certainly on the scale that we've seen in the modern world. But if one believes that we can use technology to solve those externalities, there's a world that looks a lot better at the other end. And I think the world is net better as a result of industrialization. There's less disease, there's more people on Earth because we can just support more people. And so quality of life has certainly raised dramatically as a result. Pieter, I'm curious for your thoughts on this topic. I would imagine that you're relatively aligned with Daniela and myself, but would love to hear specifics on how you think about this.
Yeah, I really like how Daniela framed it, is that it's important for people to understand that AI and robotics can bring all these benefits. We can bring it to bear to make our lives better. That's our choice. But people have to learn about it. I mean, some people see it every day around them. Other people don't know much about it yet, need to learn more. And actually, in my case, that's one of the big motivations why I started the Robot Brains podcast that you alluded to earlier, Bryan, because it's an opportunity for people to learn about all the things that AI and robotics can do and is already doing in our world, and also learn about the people who are building those robots, those AI systems, and what's their passion and what drives them. Why are they building this? And just to give you some examples, right, to make this concrete, Keenan Weyerbeck, one of the guests, he decided, we need better distribution of blood for blood transfusions in Africa. And the best way to do it is to have drones fly and deliver them. And that's zipline, and that's saving so many lives every single day, right? And Andrea Tomas, she says, okay, well, nurses in hospitals don't have enough time for the patients. They're constantly running around. They're running a logistics operation rather than spending time with the patients. But logistics, maybe a robot can, bring something from room A to room B, and the nurse can talk with the patient and make sure that their concerns are heard, that they apply the medication, take it at the right time, all those things. And so when I listen to those stories, I'm hearing exactly in many ways what I expected, but what I think many people wouldn't know is all these projects that are happening that are already, and even more in the future, positively affecting our lives. And these were just two examples, but there's so many of them that are just changing how we live our lives. And I think it's just really exciting, all these opportunities ahead. I mean, self-driving cars, no more accidents is meant to be the future. We're not there yet. I mean, Danielle is obviously working hard on helping us get there. But once we're there, I mean, that's amazing, right? How many people have had somebody seriously injured or even pass away due to an accident? And so I think there's such a bright future ahead, but we also have a big job in kind of communicating all these things and having people understand what's ahead and how exciting it is.
I'd like to build on that a little bit and say that I see a lot of misunderstanding about AI and robotics when I talk to people. And I think it's important for the population at large, for citizens and for policymakers to understand what the scope of the technology is. Right now, AI is not going to solve all of our problems, just like it's not going to take down the world. But while we don't need our policymakers and the citizens at large to understand the gory details about how this stuff works, it's useful to have people understand what a particular technology can and cannot do, and have a discussion around what it should and shouldn't do and what it must do, because at some level I think it's upon us, the technological experts, to put the technology to use for the greater good.
Yeah, I think to a certain extent, some of it is people overcoming their own perception of the ability of humans, right? They'll be like, oh, well, machine learning models can be biased. Well, humans are extraordinarily biased. It's just more difficult to understand and quantify how and in what ways. So with self-driving too, right? There's a long way to go to having fully robust self-driving vehicles, but there's some public sentiment around like, well, I'm a great driver, right? And I think there's a little bit of having people overcome the hubris of being human, I suppose.
That's right. I just want to say, for self-driving, I just want to be very clear that we're nowhere near level 5 autonomy, which is what is needed in order to have a robotaxi. But we have advanced the technology enough that we can have products that are set in simpler environments, primarily in controlled environments where the robots don't move through a lot of complexity, through a lot of dynamic vehicles and people moving around them, and where the robots move slower. So this includes factory yards, it includes ports, it includes hospitals, it includes a lot of environments where mobility, our understanding of mobility, can make a real impact today. Just as Peter was saying about the hospital scenario where you could have robots fetching things. That is an area where we have solutions that can be deployed.
Yeah, this is actually a nice transition to the last question I want to ask both of you. As we've mentioned, both Daniela, you and Peter, throughout this conversation, the sort of journey of AI and robotics as a subsection of that is one of slowly increasing the domain and the complexity of the domain in which they operate, right? So for self-driving, as you mentioned, the kind of the end goal, the domain is extraordinarily complicated, because on a road you have other people and a dog and me crossing the street, and there's all sorts of rules. It's very complicated. Versus I have a robot vacuum, and that's a pretty closed domain. It has to kind of go around my room and vacuum stuff up. So what are your predictions for 2022 and beyond with regards to domains that robotics today are just on the verge of being able to tackle? And maybe Peter, we'll start with you.
If I think of AI more broadly, right, beyond physical systems, there are many situations where AI can be applied where a small mistake is not as big of a deal compared to a physical robot. And so that's why, as I look ahead, within 1 year, I see more deployment of AI in the software world continuing to grow than in the robotics world, just because you need that extremely high reliability for a robot to actually bring value, because when it does something wrong, it physically breaks something. That said, I think there is a very clear progression happening that might not be super visible to people, but there's a very clear progression happening where robots are coming out of just being in car factories where things are extremely structured and going into not yet our homes, which I think is what most people dream of, is a robot at home. That would be a great prediction. I'll have a robot at home and it'll do everything for you at home. That's still probably pretty far out, but medium structured environments, for Covariant, that's warehouses where we're really focused, where it actually is becoming possible to be sufficiently reliable to help out. And so behind the scenes, as you click on an order online, robots are more and more likely to help out to get that order fulfilled, so you can actually get that thing delivered the next day or even same day, something we're all getting very excited about, to get things delivered quickly. And so I think that's a day-to-day life thing where robots are starting to play a bigger and bigger role, even if it's fairly invisible from where we are sitting at home, clicking on an article in a web store somewhere.
But Danielle, any predictions for you for the next year, things you're excited about?
Okay, Bryan. So I don't know exactly what will happen, but I would like to highlight 3 things I would like to see happen. Okay, so first, I would like to see new ideas for AI. And it is important to remember that today's greatest advances are due to decades-old ideas that are enhanced by vast amounts of data and computation. And if we don't come up with new ideas, then more and more applications will be plowing the same field, and the results will be increasingly incremental. So we really need some breakthrough ideas if we're going to manage the major technical challenges that are facing AI. And I guess we also need the computational infrastructure that is needed to enable progress. And this is an infrastructure that can deliver to us data and computation, just like we get water and energy today. So that's number 1. Number 2, I would like us to get serious about sustainable AI. And so let me just explain what I mean by this. So AI can play an enormous role in understanding what is happening to climate and to our planet by generating better insights, by helping us to collect data, by monitoring the oceans and the greenhouse climate. So we can use AI to have a better understanding of our climate. But to do all that, AI systems consume enormous amounts of energy. In fact, researchers at UMass Amherst estimated that training an average-sized deep learning model produces 626,000 pounds of carbon dioxide. This is equivalent to the lifetime emissions of 5 cars. And so the more pervasive AI becomes, the more of these models will be needed. So what I would like to see is more activity to shrink the model instead of growing them bigger and bigger, to get smaller models that can achieve the same as the larger models that we are working on. And there is already research that is aiming to address these problems. I would just like for this research to kind of step up and get more broader, because it's very important for our world. And then the third thing I would like to see is to get more serious about AI and privacy, because AI holds so much potential to help in so many areas, like healthcare and transportation and medicine and just about anything. And what we need to do is to ensure that technology can actually help us counter all the potential side effects that come when we use huge amounts of data, because AI requires data to do all the great things that it does. And anytime you need data, you need to consider risks to privacy. And I think that if we can get some support from technology, and if we can get good connections between technology and business leaders and policymakers, we can create the right environment that will allow us to learn from the largest pools of knowledge without risking the types of exposures that we see today.
Fantastic. Yeah, well, we've come a long way, but there's definitely still a long way to go. And excited to have both of you working on all of these problems. So Pieter, Daniela, thanks so much for joining me. Really appreciate it. And thanks for sharing all the insight.
Thank you.
Thanks for
It's been a
having me.
pleasure.